Today we will see the solution to problem 4.1 of Griffith third edition Quantum Mechanics Basic Concepts and Application. Problem 4.1 consists of three parts. Now we will see the part A, that is work out all canonical commutation relation for components of operator R and P, where actually R represents x, y, z coordinate. So the commutation relation of x with y and x with py, x with px, py with pz, and so on. And the answer is the commutation between the ith component of R, that is Ri is equal to xyz here, Pj, that is Px, Py, Pz, which is equal to minus the commutation of Rp is equal to minus Pr, which is equal to I h cross delta Ij. This is the Kronecker delta, you know it very well. And we have to also prove this. We have to prove this as well as the commutation of Rj, Ri with Rj is equal to Pi plus Pj is equal to 0. As I said, where the integer stands for x, y, z, that is Rx means x, Ry means y, and Rz means z. Now we will see the solution part. First, you take the commutation relation between x and y. So, this is equal to xy minus yx. So, xy minus yx, both are real number, so it will become 0. Similarly, the other similarly we can write it for other component also x, y, z. So generally it is the commutation between Rj with Ri with Rj is equal to 0, because instead of xy you take a xz or yz, some permutation combination of xyz, you will get same result. So we have shown that Rj, this one first, Rj, a commutation of Ri with Rj is equal to 0. So far, we have seen the commutation relation between two position operator. Now we will see the same for the momentum operator. Let us take the commutation relation between the momentum operator Px with Py, which act on some arbitrary function f, which is equal to Px, Py into f, and Py, Px multiplied by this arbitrary function f. Now you replace the momentum by its operator, that is this Px, commutation of Px with Py, which acts on f, will become minus IH cross delta over delta x multiplied by minus IH cross delta f over delta y minus uh, IH cross delta over delta y minus IH cross delta f over delta y. So this is the expanded version of the above expression. That is, I have replaced Px by its operator, which is equal to minus IH cross delta over delta x. Similarly, Py, of course, here you have f. Same thing I have done it for second term. Now you multiply this two term, this two factor, that is minus IH cross delta over delta x multiplied with minus IH cross delta f over delta y. So you will get IH cross minus IH cross into minus IH cross is equal to minus H cross squared, and delta f over delta x delta y. Similarly, the second term, if you multiply this, you will get H cross squared tf over delta y delta x. Here you can see that by the equality of cross derivatives. See, in the first term, we are making derivative with respect to y first, then x. Here, x first, then y first. So, whatever may be the case, uh, both will be the same. Yeah, we are carrying out the derivative with respect to x and y. So, these two terms are equal. See, here minus of minus will become plus. So this will be both term will get cancelled. You will get 0. So same is the case for other momentum operator. That is pi commutation of pi with pj is equal to 0. So the meaning is the momentum operator in x direction will commute with y direction. Similarly, with all direction. So it will commute with all direction. Pi with pj is equal to 0. That is the meaning. So measurement of momentum along y direction will not affect x direction and vice versa. That is the meaning of this one. So far, we have seen that the commutation between any two position operator is 0. That is I commutation of Ri with R sub j is equal to 0. Also, we have seen that the commutation between any two momentum operator is 0. That is commutation between P sub I with P sub j is equal to 0. So far we have seen these two. Now we will see the commutation relation between the position and momentum operator. So now take the commutation between Ri with Pj, which is equal to minus Pj Ri commutation of Pi Rj, which is which act on some arbitrary function f, which is equal to I h cross Kronecker delta Ij. This we have to prove it. So first take the position x and momentum along x direction. That is x commutation of x with px, which act on any arbitrary function is equal to x px f minus px x f. So now you replace this p with its operator. Then this above equation will become uh, the first term minus I h cross, because p is equal to minus I h cross delta over delta x. Of course, you have f here. Then next minus I h cross. Here I am replacing px, which is equal to minus I h cross uh, delta over delta x. Here I have shown in violet color. So now you have to differentiate x, which is multiplied by f, x, f. Here only one term, f. So what will happen if you take differentiation with respect to x, this term? Now, if you keep first term, you keep as it is. So no problem in keeping the first term as it is. The second term will become that is minus of minus will become I h cross. Minus of minus I h cross. I am taking I h cross outside. Now first you keep f out, f as it is. Differentiate with x with respect to tx, which is equal to 1. So this will become only f. Then you keep x as it is and differentiate f. So you will get x tf delta f over delta x. Now you compare this first and the third term, which will get cancelled. Only this I h cross f second term will remain as it is. That is, the commutation of x with px is equal to I h cross f. The second term only retained. Then the first and the third term will get cancelled, which implies the commutation between x with px is equal to simply I h cross. Just now we have seen that the commutation between x px, that is momentum along x direction, is equal to I h cross. In a similar way, we can also prove that x px, which is equal to y py, which is equal to z pz. That is, these three commutation will become I h cross. That is x component, commutation of x component with momentum along x direction, y component momentum along y direction, z component momentum along z direction is equal to I h cross. All three commutation become I h cross. Now we will see what will happen the combined term. That is, now we will see that x commutation of x along with the momentum at y component of momentum, which act on some arbitrary function f, which is equal to x py f minus py x f. So now you expand the right hand side by introducing the operator part py. So which is equal to I h cross x. So x I am taking as it is. Then this p f, that is py is delta over delta y, and this f will come here. Similarly here py can be written as minus I h cross delta over delta y, which acts on x f, which I have shown, the second term I have shown in red color, sorry, violet color. So now you keep the first term as it is, you expand the second term. First you keep x as it is and differentiate y, sorry, differentiate f with respect to y. So that will become delta f over delta y. Next, what you are going to do is you are going to keep as usual f as it is. You differentiate x with respect to y. That is, if you differentiate x x with respect to y, then naturally this will be 0. If you differentiate x with respect to y is equal to 0. So the third term will be 0. You will get only these two terms. Here minus of minus will become plus. So if you compare both the term, first and second term, this will become 0. So the commutation of x and momentum along y component of momentum is equal to 0. So we have seen the commutation between x with py is equal to 0. In a similar manner, we can also prove the commutation of x with pz is equal to 0. That is, the commutation of x with py and the x with pz is equal to 0. That is, the x will commute with momentum along any other direction, not with x direction. That is the meaning of this. See, we have seen already that the commutation of x with px is equal to I h cross. In a similar way, we can see that the other component also, that is the commutation of y with px and the commutation of y with pz is equal to 0. Similarly, the commutation of z with px, the commutation of z with py also equal to 0. Hence, we can generalize this as Ri with Pj is equal to uh, minus Pi Rj, which is equal to IH cross delta Ij. That is, when I and j are the same, then it will be IH cross. Otherwise, it will be 0. That's what we have proven so far. So that is the proof we have seen now. We will move on to the next division. In section P, we have to prove the Ehrenfest theorem. That is, in three-dimensional Ehrenfest theorem, the time derivative of expectation value of R is equal to 1 over m, the expectation value of momentum. Similarly, this is first theorem. Second theorem is time derivative of expectation value of P is equal to expectation value of negative gradient of the potential V. So now we will see the proof for it. That is, first you take x along x direction. The time derivative of expectation value of x is I over h cross expectation value of commutation of h with x. This is by definition time derivative of any operator is equal to I over h cross expectation value of commutation of Hamiltonian operator with that particular operator under consideration. Now you try to find only the commutation relation as a first step. That is commutation of h with x, which is equal to p squared over 2m plus v, which commit we have to find the commutation of this with x. Now the potential energy purely depends on the position operator. So v and the x will commute, so we can cancel the v. Now the expectation value of x with h is equal to 1 over 2m. I am taking out because it's a constant. The commutation of p squared with x. So the commutation of h with x is equal to 1 over 2m p squared, commutation of p squared with x. By the definition of commutation, that is p squared over x, can be written as this 1 over 2m I am keeping outside. This p squared can be written as px squared plus py squared plus pz squared with x. Uh, so this commutation we have to prove this. Now we have already seen that x will commute with py and pz. So we can cancel this. Only x will not commute with px. So I am retaining this px squared only. Now this in turn turns out to be the commutation of h with x is equal to 1 over 2m px squared with x, commutation of px squared with x. Now from the commutation relation, we can write p squared with the x is can be written as px, you know, from commutation relation. Px with the commutation of px with x and commutation of px with x multiplied by px. This is using the commutation rule. So using commutation rules, we can write like this. Now the commutation of px is equal to IH cross. Here one IH cross. So this will become IH cross px plus IH cross px, which is equal to 2 times IH cross px divided by 2m. So here this 2 will get cancelled. 2 will get cancelled. You will get minus IH cross over m px. So by definition, the time derivative of the expectation value of x is equal to I over h cross the expectation value of commutation of h with x. Just now we have seen the commutation relation between h and x, which is equal to this I over h cross I am writing as it is. The commutation between h and x is equal to, just now we have seen, minus I h cross over m px. This violet color I am replacing by this violet color. Just now we have seen the commutation between h and x. So now you can take I minus I into minus I will become 1. And similarly this h cross and h cross will get cancelled. So only 1 over m, you can, since it's a constant, you can take out 1 over m, the expectation value of px. Hence we have shown that the expected time derivative of expectation value of x is equal to 1 over m the expectation value of px. So similarly we can do the same thing for y and z. So we can write generalized expression, time derivative of uh, expectation value of r, where r represent x, y, z, is equal to 1 over m expectation value of p. So this is the first theorem. Then now we will prove the second theorem. Similarly, the time derivative of expectation value of momentum is equal to, by definition, I over h cross the expectation value of commutation of h with p. Now our task is to find the commutation between x and p. So the commutation between x and p, h and p is equal to h can be written as p squared over 2m plus v, the commutation with p. Here, the p and p will commute, so this can be get cancelled. So you will get which is equal to the commutation between v and p. So as usual, uh, let the commutation h and p act on some arbitrary function f. Uh, that is h is replaced by v from this expression, above expression. The commutation between v and p is equal to vpf minus pvf. So now you can expand the right hand side. That is, p is replaced by its momentum operator. So the momentum operator, I am taking IH cross as common. So first term will become v times the derivative of f with respect to x. That is delta f over delta x. Similarly, the second term, the p, I'm already I have taken minus IH cross outside. So delta over delta x v f. This I have to expand now. So we have just now seen that commutation of h and p, which act on some arbitrary function f, can be written as minus I h cross. This p is we have replaced already. Only thing is I have to expand this term. So if we expand this term, first you keep v as it is. In the second term, first you keep v as it is and differentiate f. So delta f over delta x. And next, what you are doing is you keep f as it is and differentiate this v. So you will get uh, delta v over delta x f. Now you can see the first two terms. First two terms are equal, so that will get cancelled. This and this will get cancelled. So only third term alone left out. So here you have minus IH cross, here minus. So which will become plus IH cross. then it can be written as simply I h cross delta v over delta x f. So which implies that the commutation between h with p is equal to I h cross delta v over delta x. So by definition, the time derivative of the expectation value of p is equal to I over h cross expectation value of commutation of h with p. Now we have found that the commutation between h and p is equal to I h cross delta v over delta x. I am replacing that here. That is the commutation between h and p is equal to I h cross delta v over delta x. Just now we have seen. So here h cross will get cancelled with this h cross. I into I squared, which is equal to minus. So this will become minus 1. I into I is equal to minus 1. So that will become minus, in the right hand side, it will become minus delta v over delta x, which is nothing but the negative gradient of v. So negative gradient of v. That is time derivative of momentum is equal to the expectation value of momentum is equal to the expectation value of negative gradient of potential. So v. Uh, this is the Ehrenfest second theorem. So in the third part, we have to formulate the Heisenberg uncertainty principle. So according to Heisenberg uncertainty principle, sigma x into sigma px is equal to or greater than h cross by 2. Here I like to spend some time. See, you cannot measure the position and momentum in the arbitrary accuracy along the same direction. That is the x direction of momentum, and x cannot be measured accurately simultaneously. Whereas the position, yeah, along x direction and momentum along y and z direction will come. That means uh, the momentum along y and z direction and position along x direction can be measured simultaneously accurately. So only along same direction of momentum and position cannot be measured accurately. That point I like to highlight here. We can write it in a generalized way, that is sigma x over sigma px is equal to or greater than modulus of 1 over 2i, the expectation value of x with expectation value of commutation of x with px. This expectation value, it is we are taking modulus. You remember that. So it sign does not matter. So the commutation of x with px is equal to I h cross. Though I have written the expectation value, h cross is constant. You can take out of the expectation value. Now already there is 2i in the denominator. I will get cancelled. So you will get h cross over 2. Uh, so generally we can write that sigma ri into sigma pj is equal to or greater than h cross over 2 multiplied by the Kronecker delta ij. That is, when ij are different, it will be 0. When ij is equal to this, I and j is equal, then it will be 1. So this is the generalized uncertainty principle formula. Here R I refer x, y, z. Here J also refer x, y, z. Thank you very much for watching my video and supporting me continuously. Thank you very much.